Morning, guys. It's 12:16 in the morning. It is the 24th of November, 2023. We were trying to see Roseman, California. Okay, turkey holiday over, but try this cosmic turkey for you. You ever heard of cosmic rays? A long while ago, early in the 20th century, they were experimenting upon radio, listening to traffic. First time ever to invent something that'll transmit messages from one place to another place using radio waves, energetic particles that we use on a constant basis to transmit data from one area to another area. We talk in a radio, the sound waves in electronic form would travel through our atmospheric ether and picked up by our receiver station. I understand about radio astronomy and radio electronics. But in that electromagnetic ether that we travel our data through on a constant basis, our zeros and ones that we throw out from our transmitting station, a laptop, for instance, cell phone, we depend upon this ether, as I call it, to have information transmitted to and from. I transmit something. Um, it goes out to different receiver stations and gets to be repeated all over the place. If we're doing data transfers, it's zeros and ones electronically coded in these packets of energy. And in these packets of energy, as I said before, coded for zeros and ones, but somehow, somebody actually figured out what things beyond that, beyond our own transmission is. We're looking beyond, and we don't even see it until we actually pick up on the transmission, and there it was. Cosmic rays. For the first time, we actually, back in 1916, I think, we picked up on energetic particles beyond what we thought. We're just getting started with radio transmissions. All that energetic static that you hear, atmospheric, constantly bombarded by low level energy particles from the sun. Took us a long while to figure that out. But better than that, we started building up receiver stations all over. Took us time. But we're getting so much energy from the universe, information actually, in the form of energy particles, that it amazes us that the universe is alive in this kind of energy form. And in this energy form, we're discovering that astronomical objects emit this kind of energy. And it's mind blowing when someone gets into radio astronomy and into particle physics. And they started detecting all these nice, juicy energy coming through. Is it affecting us one way or another? Our atmosphere kind of protects it. From what the scientists have been telling us for decades, so as long as their explanations and analysis with their multiple detectors and satellites being sent into deep space to receive this information, see what's going on. But we also have our radio telescopes, big ass antennas in different forms to listen in to the universe. We can listen to the sun beating us like crazy with the cosmic rays. We can listen to the planets emanating their own siren song in the space. There are clips of this information out there on NASA concerning about how these planets are emanating in our own solar system that they've picked up. But what if you happen to get a high-speed message from deep space? Where is it coming from? Where is it coming from? We have been detecting humanity these kind of energy projections but we don't know where the hell they're coming from specifically. We know the general neighborhood. We already know that within a lot of data that they've been trying to research left and right, there are different universities in the United States and also in Japan are coordinating with each other. Because I've already seen the news being published already yesterday morning in the science sections of our newspapers and our news media organizations out there. Buried, but they're publicly stated anyway, that we've already detected high energy particle cosmic rays. Okay, you're scratching your head on that one. High energy messengers, I would call them, from beyond. Now, keep this in mind. Get a visualization in your head. The universe is pretty damn big. Places that we know that would create energy is by stars exploding, um, something squeezed out of existence or nearly squeezed out of existence through uh, gravitational collapsars that they still call black holes. Suck the thing into itself, and it screams out its energy signature out of the black hole, saying, "Help me!" Behind the speed of light, just racing right out of the damn thing. We caught gamma energy bursts like that. But somewhere, and they call it the local area void. And that's something interesting, isn't it? Because I just caught that one, and I never picked up what the hell it is. Give me a second. I'm going to get a Google search on this one real fast for you. Doing a Google search on artistic impressions and composites of radar images and whatever we can. There are areas outside our galaxy. In fact, the universe is clumped in different formations. Of what life is supposed to look like. Or groups of neighborhoods actually, in the ever-expanding universe. And for billions and billions and billions of years, we got formations and we got echoes of formations. Renewing and revigorating itself and then destroying itself. Because of the cosmic vacuum cleaners, the black holes, are sucking things up left and right. Now we can look outside with our telescopes and we can see the vastness of it. But beyond the vastness of it, there is holes out there. Beautiful, extreme, and scary. Because the more we keep learning about our own neighborhood out there, the galactic neighborhood, the more it is more what we think of. There's a lot of artistic impressions, but trying to get specific information of what these voids look like. Okay, voids look like a hole. Localized area. Let's say you got communities around a certain area, but sporadic neighborhoods. Okay, let me throw something out to you. Desert communities. Because of resources, we can build our communities. Take a look at Google Maps at the Antelope Valley. We'll use this as an example here. You got it? Get a little. I got that. Okay, got that angle there. Okay, in this area, this vast area, we also have expanded areas. But there are certain isolated areas in the Antelope Valley that we're still trying to populate. But they're also isolated. You can look at the inner areas and see where the isolation spots are that they haven't been developed. Consider these as terrestrial voids, temporarily. Now, these areas are probably lacking resources, or probably wasted resources, or probably got hidden resources we don't even know of. So we can develop these areas, but put this in a concept that this is space, and these areas don't have resources, nothing to build upon, nothing to create life of sorts, or just create planets or systems or a galaxy. They are so devoid because they may be having areas that they're expanding. Now, in our terrestrial experiment here, we have it collapsing upon itself because we're sucking up the resources and we're putting in resources. We're putting in um, places and areas to suck things out of it. We're creating our community, trying to make it more and more and more until we have it homogenized. We have it populated. But not in deep space. Deep space is different. The universe, as we keep discovering on a day-to-day basis, year by year, century by century, it's pretty damn big and expanding like crazy. And if they got enough resources around it, we can get solar systems and galaxies created. Definitely not in our lifetime, but it can be created as long as we got it. We also have to have enough sufficient force of nature to have these clumps be solidified and held together. Gravity. We have to have gases floating in the area, either recreated or maybe still originally out there, that can be generated into life, as in star formations. And therefore, we would have nurseries being built. Now, because our own galaxy right now is in constant flux, we do have cosmic cleaners sucking things out, but there's also predicted to be white holes still producing matter. We also have a cosmic gravitational life sucker in the middle of our galaxy. But it's still emanating energy and still allowing creation of life-giving matter beyond its accretion disk. But the gravitational force is still there, spinning our galaxy around, allowing other places to get commingled and fixing out their communities until one of these here days, the gravitational force, I would think, in my own limited knowledge of astronomy, would be sucking the galaxy and everything else right into the hole, and there goes oblivion. We don't know if that's going to happen right now or any other time soon, but for right now, for us limited series of human beings, so limited beings that we're dealing with our own finite time. So in our own finite time, we're seeing the infinite being displayed to us. We are seeing energetic particles bounced around across the universe. Now, how is that possible? Well, said before, you need to have an energy source. You need to have something that creates the big push-off of the particles. And these particles, cosmic rays as we call them, because they are going as fast as the speed of light. And there's also other particles we discovered that are faster than the speed of light. Now, I'm not hip on the astronomical terms concerning about the cosmic rays and what they're called these days, but I get the gist of it. The speed of light is a constant barrier, and mankind's been trying to think of how to get past that damn thing. And nature, in its own way, that we keep discovering, with enough sufficient force, particles are going beyond energy particles, maybe in waves, are pushing things beyond it that we are picking up right now as it is. Neutrinos are one of those energy particles. We have neutrino energy detectors. Europe and Japan, United States, Probably, I think, Australia if we're lucky enough to get the southern area. Because I also know that we've got smaller experiments out in the Antarctic in different stations that they would all monitor what the universe is doing. Once we get those energy particle detectors activated, once we get a knock on the panel's door, say, "Here I am. I just came from over here. I just came to say hello before I go streaking through your planet, so don't mind if I just streak right through." Low energy particles can actually do that. Go right through your hands if you're not careful. You don't even know it. We're not even aware that we're bombarded with enough low energy particles from our own sun that we're constantly feeling it, not even feeling it. It's just you don't even know what's there. But high energy, that's a force of nature right there. Getting back to the local void there are multiple pictures on Google I'm looking at, different artistic impressions, but they're still fascinating and terrifying at the same time. Because they're telling us there's one area or certain areas in the local group that we've got, or even beyond the local group, that we've got void where there's no observable action going on. We have to observe it to understand it. We need to see it, either by radio waves, by looking at our detectors, or we need to visually see it. Now, we understand speed of light only is a constant at this point in the universe, but it can only go so far and so fast because of the distance of space we have right now. When I see any lights in the sky, I know we got stars millions of light years away from us, or thousands or hundreds. And it took them that long, light year. They only travel so many percentages. Hang on. Okay, so you're going to be asking me about that one, aren't you? That's the speed of light. Okay. Hear my fingers typing on the keyboard here. Okay, what we know and observed and hasn't changed yet, according to what space.com has been indicating, the speed of light is exactly, hold on to your brain stems, 299,792,458 meters per second. That's about 186,282 miles per second. A universal constant per second. That is the speed of light. Light year is a distance. The light can go at its limit, the particle of it, or the wave. It's both a wave and a particle, according to physics. And it takes a lot of this light year to reach us. We can visually go outside and see, we think the stars are there, but they're not. Or they still could be. But since light's only traveling at the speed that they're limited to, the energetic particle limit that they are actually maxed out to, that's what we're viewing. That's what we're seeing right now. We have 8-minute distance between us and the sun, but we've got millions of miles away from the sun. But in light distance, we got about 8 minutes light travel. As I said before, we got 186,282 miles per second. We got 8 minutes distance using the calculations of that one. Of the light particle emanating from the surface of the sun. I'm not talking about deep inside the sun. I'm talking about on the surface. To hit our atmosphere. If the sun happened to went nova right now, we won't know about it until 8 minutes later. The energy from the sun would be expanding so much it'd be throwing off particles left and right. And if it had sufficient enough mass and energy on that one, it'll be screaming out to nearly the speed of light because of the energy and force. But we're talking about something of an energetic cosmic ray here. We're talking about millions times force on this one. But coming from the local void? See, that's the thing I can't wrap my head around. Why? If we have an area devoid of matter and we actually had an explosion, it would take millions and millions of years of our time that we'd be able to observe something. The Crab Nebula, I'm going to use that one as an example here. Give me a second. It's famous, isn't it? Basically, the Crab Nebula was a supernova explosion that happened millions and millions of light years and in a distance at this point. It's very photographic. It's very pretty. And it's a long way from us. It's about 6,500 light years away in the constellation of Taurus, according to NASA.gov on this one here. Okay, 65,000 light years. Equate that to our own time right now of years. So, in humanity terms, we'd seen it. We would probably recorded it, put it in a cave drawing or something like that, or an etching somehow. It got scared as hell. But we'd seen it in our lifetime because it was that close. The closer we are to the object, the more we're going to be able to see a thing. Let's say, for example, if Alpha Centauri had a burp, blew itself up. Light years on that one, about 15, 20, I think. Hang on. What was that one? Okay, Alpha Centauri star system, we're talking about, again, according to NASA.gov, it's about 4 light years. Okay, so it's going to take about 4 years for the explosion to hit us. Not to mention whatever kind of cosmic rays are going to be forced out of that thing. Now, if it's going to be traveling at the speed of neutrinos, which are faster than that, traveling that fast, we'd be able to get the damn energy long before then. But it'll take 4 years for that energy to hit us. That's one of the closer star groups we have out there. Blows your mind? It blows my mind every time I keep learning something new about astronomy that I never knew about. But there's a lot to know about the universe, how it works, why it works, all the math involved. You can look at it and see how pretty it is from the planet we live on. We can observe the dying light of different stars, millions and millions of light years, and if they actually blew up, it'll take us a long time in humanity terms to look at it if we're still alive or traveling at that point. The closer the stars are, the more action we'll see. But the cosmic rays that came out from a local group, a void, now that I can't buy. In the direction of it, I can. But if there was any neighboring star systems outside, or maybe around the peripheral area of it, I can understand. And if they're looking for nebula displacement, if they're looking for gaseous displacements, maybe smaller or larger ones that they can actually detect by radio or by visualization, that would probably give the scientists something to work with. But if they just detected it's coming from a local area that's totally void, the question is, why? The only answer that pops in my head at this point would be a gravitational singularity, the black hole. But even then, it would be emanating energy out of it because the accretion disk, before the stuff goes in to the black hole, is heated tremendously so that it will be able to detect anything. But this is what's driving the scientists crazy when they publish this. Where the hell is it? Where is it from? We know the direction it came from. Question is, did it come from the other side? There are billions of light years between edges on this local void we're talking about, between a galactic group and another galactic group, somewhere in the middle, or maybe somewhere in there. Maybe from the other galactic group managed to kick out their cosmic particles in our direction one way or another. Possible. But this is the thing that kind of woke me up this morning. Not by the article itself. I woke up anyway, shortly before midnight, and I started searching through stuff. But when I saw this one, I'm like, hello. I had to talk about it. So it's something that I'm still going to have to. I'm going to have to get more information on and put it into my terrestrial limited report in a menial class of math liberal arts. And then I have to somehow put this away. But information like this I'm putting away in my head because I'm also saving the PDF files because I want to read this stuff a little bit later on down in life. I collect things. I collect the information. I collect data. It's not bad being a collector sometimes. You learn more stuff. But the more stuff I keep learning about, I have to keep understanding what's going on. So, the search for knowledge continues. I may not be the greatest mathematician around. There's no way in hell I'm going to be that way. I may appreciate math. I may appreciate the numbers happening and the numbers telling us that things are flowing in this particular form and fashion. Fractal stuff. Okay, stuff I have to talk to the professors about, and we'll hammer things out and see how things are going. I wonder how my math professor would understand high energy particle physics and explain to me how a cosmic ray showing so much energy, so much power. That's the thing. That's the thing that catches me. If we're talking about the local group, if we're talking about within the galaxy, if we're talking about something, we got gravitational forces left and right. We've got ways of probably deflecting the energy, maybe keep forcing the energy going. If it's that energetic, it had to have an ejection point. Something about our understanding about the laws of physics. I can thank Newton for that one. Newton. He and his observations, if we didn't have his observations or Galileo's understanding, or even Copernicus, we would not be understanding what we're understanding today. Sometimes math is fun.